Hello everyone, welcome to the day 9 of the LLM Mastery course. Today we are going to see about collecting different data and processing it and then creating a torch data set and a data loader for pre-training mini GPT-2. We already built mini GPT-2 yesterday, and today we are going to see how we can process the text in different formats so that it is possible for pre-training. All right, so that is the aim here. The installations will be required are just data sets, and that's all. Just data sets enough. And for this you would need some things. For example, you would be required to mount your drive. Make sure that you mount your drive because the data will be pretty huge. You can't do the whole thing in Google Colab itself. You'll be storing things in local. So for that, it is better to mount Google Colab so that we can store the datasets there. So for me, here you can see my dataset is now mounted. I mean, my drive is now mounted. I have taken the liberty of searching the dataset prior to the session because this will involve a lot of uh, time, like to understand data and then process it. If I show everything in live, it will be delayed for you all. So that is why I've taken the liberty of exploring the dataset offline. So here you can see I'm using a dataset known as CC OpenWebTX. So if you're wondering what is OpenWebTX, OpenWebTX is the dataset which is used by GPT-2 for training. Like OpenAI used this dataset for training, but we are taking a subset of that. Okay, we are not taking the whole real dataset from there. Rather, we are taking the subset of a dataset which is available in Hugging Face. Okay, thanks to the person Kerem, whoever it is, because they are making our life easier. Because without them, it will be harder for us to make a sample like this because it is around TBs of data. Okay, so right now we are having 1 lakh samples here, which is text and target. So this was a good data set actually. It was saying if there is a text and there is a text which is positive or negative. Okay, that is what is this data set all about. But we don't need sentiment analysis here, right? We need data being generated, like story kind of a generation of one token after another token. So target is not required here. We are removing that column. We are seeing if the dataset is having the say only column. Yes, it is. And then we are running the um, function which is known as save to disk, which will basically what it will do is it will store the arrow files in your local, for which they have used an implementation known as fspec. Basically it will be like cache. Okay, it will store like and then it will be loaded in an instant actually. So it is a very good format to store if you are having temp data. Okay, like temp means intermediate data. So this save to disk, after this I'll be changing it. It's not a rigid format. Okay, I'll be processing it further. So for that cases it is better to use save to disk. Okay, now there is another data set. So OpenWeb is a old data set, let's put it that way. It is 5 to 6 years old, but there is a very new data set in Hugging Face which is created only for pre-training, and you can see it is better in length and the format looks even more better than how it was there in OpenWeb, because this is a data set created by Hugging Face especially for pre-training, and this even outperforms the major pre-training datasets which are there in the hub. Okay, so let's see how we can use this. So the dataset name is FineWeb 100K EN medium. Okay, and if you see, it is not there from Hugging Face because this dataset actually has TBs of data again. It is even more in size. For example, it has around 5 billion pairs if I'm not wrong. Just pairs, I'm saying 5 billion pairs means 5 billion sentences, and in 5 billion sentences it will be trillions of tokens. We can't load that even in our local, right? So I thought, okay, let's take a sample, and luckily there was this person who had 100K sample, and then I'm just using that. Okay, So you can see now it is loading, and this is a sample data. But here if you see, we have only text, which means we are good enough to go for the next step. You guys need to run this, okay, cp-r pretrain, because we are saving things in pretrain. Okay, make sure that those are mounted in drive, because with Google Colab at any given point of time you might go out of memory, out of session, things like that. It is a very irritating aspect. So what you can do for that is just uh, put it in your drive whenever possible. So for example, right now data is downloaded, data downloaded stage is uploaded, something like that. Okay, um I already have um, those in my drive. So what I'm going to do is I'm just going to start with data processing, and here if you see in data parts I'll have something like a process final JSON data, but those are not required. Okay, here what I'm going to do is data parts is to 2. Okay, if I give that sorry, this is how you will get. Make sure that you comment these, okay, when you execute. Here I'm concatenating this data set so that both are concatenated, becoming a single data set. For that there is one condition, that you need to have same column. For example, here there is only one column, that is text, and it is a common column. All right, so make sure that you have a common column, and like everything is having the same structure, something like that. So now the data is combined, and here you can see it was 1 lakh and then 99,996. So it became 1,99,996. Looks like an offer number. Like it is always good enough to first convert it into pandas, to do only one thing, which is to drop null values, because with open source dataset there is always a possibility for null values. And here if you see, um it is 1,99,996 rows, and if I put this now, it is 19 rows, which means there is around 87 rows, yeah, 87 rows which has null value, and that is very harmful, right? So that is very important. Make sure that you remove duplicates. For us, there won't be any duplicates, but if you want, what you can do is just do pretrain data df equal to pretrain data df dot this will drop only exact duplicates. Okay, duplicates. But like if you are seeing some closer kind of duplicates, it is upon you to you know write a logic so that duplicates are removed. So right now our job is to make the life of the model easier so that it will learn faster and give us a better result. That is the aim here, right? So here what we are going to do is we are going to just normalize the text so that um you know it will understand that okay, it need not generate any capital letter, so the learning curve will be a lot easier. And also I'm just taking the first 2000 characters. Okay, that is what this normalized text does. Okay, here you can see my data set is there. I'm mapping a function. uh, so basically what it will do is it will go through each rows, and in each row it will apply this function. Okay, that is what happens with map function. Here in this function what I'm going to do is I'm taking the text column, I'm lowering it, so everything will be in lowercase, and here I'm taking the 2000 character. Why? First, uh, if you see, we consider our context length to be 256, right? At some point of time we may make it 512, that is for the later stage, but we are considering it to be 256 right now. So the words approximately which would be there in this 256 token would be around 170 to 200, because there is a, let's say, unwritten rule that the tokens will be words into 1.5 times, like for example, if it is 170 into 1.5, which will be 170 plus what it is 85, so something like 255, something like that, closer to that. So it is 170 to 200 is what I'm expecting, and the average word length would be around 5. Okay, so 5, so it will be 200 into 5, which will be 1000 characters, but we are providing 2000 because if we think, okay, I'm gonna run it for 512 context length, this will be even supported. Why I'm doing this? Two things. One, it will be lesser in context length, and it doesn't make the model life easier. That, let me put that way, model life easier is making it lowercase, but when you make it shorter, your storage will become lesser, right? Because these will have let's say 15,000 characters. That kind of image samples also will be there, but we don't need that, right? We are supporting only 2 to 6 context length. Why do we need to store extra data? So we'll just remove those. Okay, and if you combine those, with the map function, you will get a new data set. That is what I have written here. You can just override the same data set as well, that is your wish. If you run this function on this data set which we created from the pandas data frame, where we dropped our nan values, which is missing values, we get this pre-trained data processed. Okay, here you can see it took me around 24 seconds for just 2 lakh rows. Imagine a billion of rows, it will just take days, as simple as that. Here I'm gonna add a column. Okay, it is always best practice to do that. Why? I'll say that later. Have, once you combine things, or even if you have a single data set, make sure that you add a id column. For me it is simple data set here, so I'm just using index kind of a function, but in real time you should use something like a uuid number generation. Okay, if you put in Chrome itself or any browser you have, or even ChatGPT, stating that generate me a function to uh, like you know generate a UUID number, create a function to do that, and ChatGPT will give you that. It is very simple. In Python itself, there is library for that. Why it is there? Because in real time, if you'll have that many number of data, right? For example, I said millions of rows. Let's consider in that way. It won't be enough for you to store in your RAM. Okay, you can't load the whole data set. So what I usually do is I'll store each data set as a JSON file. Okay, so for that, what I use is, for the file name, I'll use ID. Okay, that is why I create ID column. But yeah, it is your wish. If you want, you can do that, or generate the ID at runtime. But it is better to have as a metadata in your data itself, so that at any point of time, if you want, you can just check your ID where it failed, something like that. Okay, that is why it is there. Now let's run these. So it is taking around 30 seconds here, you can see. And here we'll also add the ID column, like I said. And once that is done, I'm not going to save it, but here you can see again it is a milestone, right? It's like a checkpoint. You have processed your data set, you are added your ID, it's like closer to your final data set. So what I'm doing is I'm saving to the disk as process final, but I have it already, so I don't require that. But you make sure that you execute this as well. Okay, guys, don't worry, just data collection and data pre-processing alone happens in this walkthrough kind of a format. After this, again, like, we'll code everything in live only, so you need not worry about that. So here, data processed, which we created here with columns added, id, we are just shuffling it. Okay, we are making sure that the orders are different, because the way it is concatenated is, the first datas will be about, um, let's just say the first datas will be about open web text, and the second data set will be about fine web, because that is how those are there. Here we are shuffling it so that it is not in any order, it is in a random order. Okay, so just giving some difference to things. So now I'm just selecting the first 10,000 rows because we are not doing real pre-training. We're just doing a mini GPT-2. Okay. So I'm just taking the first 10,000 rows here. That is what happens in select, and that is why we shuffled. Okay. To make sure that we take data from both. And here you can see I have a function to save rows as JSON. I'll go through each row. I'll take the row of ID, I'll convert it as string, and I'll add it as .json, and then I'll store it with combining to the saved path. Okay, so for that, here you can see there is a function which is pretrain slash final slash JSON data. That is where I need to store. So if I run this, it will create a directory if it is not there, and it will save there. Okay, make sure that you execute these two functions as well, so that your final JSON data is also stored in your drive, so that you can download it and continue the session in VS Code how we are going to do right now. Let me see you with data loader and data set. Right now our data pre-processing and data collection stage is completed. Next we are moving on to touch data set and data loader.
Hello everyone. Since our dataset is now ready, which is collecting it and processing it, I've loaded it in my local. Here you can see there is min GPT-2 pre-trained data, which was the data we created there. In that, there will be a folder known as final JSON data in which all the JSON are available. So right now, I'm just going to create a file which is GPT-2 dataset.py. All right. So when I create this kind of a file, you might know by now that we are going to create a torch data set and a torch data loader. Okay. So these are very simple. You need not worry about anything here. Let's start with some imports, which are very important here. From torch dot utils dot data import. I hope it will be visible. Let me zoom it a bit for you all. Yeah, looks good. Um, from torch.utils.data import data set and then data loader. Okay, these two are needed. And then from transformers import GPT-2 tokenizer because we need that tokenizer. Okay. Um, let me check if there is my mistake in that. Auto tokenizer is there. Okay, let me use that. That is not an issue here. And here, if you see, we have everything as JSON files, right? So we need to use those JSON path. So for that, we need glob. Okay, we need to get all the file paths. So from glob, import glob, and then import JSON. Okay, these are the imports which are required. Right now, let's create the data set. First, let's start with creating GPT-2 data set. And that is going to be a torch data set. So we are going to override that, right? So first, we are going to create that def dunder init, and it is done the super init. Thank God. Um, right. So in this, we need a few things. First, get the data path directory here. So that is going to be a string data path directory, and that is going to be a string. Followed by that, we also need a tokenizer, like I said, and that is going to be the auto tokenizer, which we already got. Okay. So here, self dot data paths. Here it is just directory, right? So we are going to do a glob of data path directory plus star star. Here it is under the assumption that you provide the data path directory with the slash. Okay. Um, Next, we need to get the tokenizer. Self.tokenizer equal to tokenizer. Self.tokenizer dot pad token will be equal to self.tokenizer.us token. Always remember to set this and then max length. Self.max length is going to be max length. Okay. So max length is something we need to get here because we need to truncate and pad it to that number, which is by default 256, but we can override it. Okay. Here the important functions, if you remember from our prerequisites video, are length, for which here the data points, there is one data point per file, which means len of self dot data parts is more than enough for this. Okay. And in here, in get item, def under get item self comma index, what do we need is, first we need to open the JSON file at that index. Okay, with open self dot data paths of, let's put it as, for me, I feel weird of using index. Let me have it as idx. Self dot data paths of idx. It is gonna be in R format as f. Content will be equal to JSON dot load of f. Here, the text, which is our input text, will be content of text. All right. And then we have tokenized inputs will be equal to self dot tokenizer of text, where we'll be giving padding equal to max length. Basically, we'll just pad it to 256 if it is not there. Truncation will be set to true, because if there is a value, I mean, if there is a sequence which is uh, bigger than max length, then that also would be, truncated to 256. And then we'll have max length provided, which will be equal to self dot max length. And then return tensors. This is another parameter which is just to provide the tokenized input as tensors. Okay. And that will be PT. All right. So now tokenized inputs of input IDs will be equal to tokenized inputs of input IDs, because it will consider a batch, but we are not batching it. We are batching it later. So first we'll squeeze it so that the first dimension goes off. Okay. And here the labels and input IDs are the same. Okay. Because basically you're going to finish the same, right? So here, sorry, the labels will keep it the same as input IDs actually. Okay, because basically if you see, we are just predicting the next token, which is to replicate the ground truth, right? So the ground truth, which is the input sentence, is going to be the same here, but inside we'll do something known as shift right, so that it forces to see the next token. Okay. Right now it is going to be input underscore IDs. Okay. And once that is done, your tokenized inputs is ready, which means we can just return that. Okay. Tokenized inputs. So here you can see our data set is ready. A simple but easy to create and a powerful data set. Let's put it that way. So here it is, create train data loader of data path directory, and then we are providing max length, which will be equal to 256, and then we'll provide a batch size. Right now let's consider 1. Okay. And then shuffle, it is another parameter, we'll set it to true. Drop last, it is again a parameter for data loader. Let's consider that to be true as well. Basically what it will do is, if there is batch size 2, it will try to combine the values in the data set, and then it will see like, okay, there is one thing missing, so I'll just drop it, that batch. Okay. So that is what is that. And then num workers, data loader num worker, I don't have a very big computer or GPU or CPU, so to speak, so I'm just keeping it to 1. Okay. I don't have that many threads to work with. So tokenizer will be auto tokenizer dot from pretrain of OpenAI community, if I'm not wrong, slash GPT-2. And then here, first I'll create GPT-2 dataset equal to what? GPT-2 dataset of data path directory, which we already got here. Max length, we already got it here. And then we need the tokenizer. Okay. Tokenizer and then max length. Yeah. So now it looks good. So we need to create a data loader. Um, if you see in pre-training, we don't do a lot of evaluation loops because it will delay the pre-training. Okay. So for that, what we usually do is we take a sample, a checkpoint, and then we'll do evaluation loop on that, so that it doesn't disturb the pre-training. So that is how I'm just going to keep here. There is not going to be an evaluation loop. So here for data loader, we are providing the batch size. We are setting the shuffle to true. Drop last. uh, I'm just adapting to this new keyboard. Drop last. Again, it is going to be drop last to true. Num workers is going to be num workers, which is 1. And then here I'm going to return this data loader, and that is how our data loader is going to be ready. All we need to do is now create in the model, there are going to be some changes which we need to do. So for example, I did this one change, which is to return the attention weights. Previously I used scale.product attention from torch, right? Instead I use their direct function, so that we can return the attention weights for ourselves to visualize. Okay. So you can see attention weights is also returned in that way. So yeah, that is one change which I did. Now, what I'm going to do is, first, I'll show you how to create a simple training pipeline, which is not very complicated. It will be around 100 line of code max to max. And then what we'll do is, I already created, for one of my pipelines, I already created a very complex, a training pipeline, which has all the capability in it. I'll provide you with that code, and I'll show you, I've just adapted it for our pre-training. I'll just show you that code. I'll just give you a walkthrough so that you guys will be able to use it. Okay. So let's first create a file, let's say put it as dummy train.py, because like I said, this is not something which you can use for pre-training directly, but this is how you need to start a training loop. Any training loop you write, it should start from here, because this is going to be the base, and you'll be adding functionalities on top of this actually. Okay, so let's see how to create that kind of a training loop first, and then we'll move on. So now let's create the dummy trainer, for which we need to import a few from GPT to config. Import star, because for this I have kept some config. Here you can see number of epochs, learning rate, batch size, weight decay. All of these are provided there. Those are there. From GPT to data set, we'll be importing, sorry, um create train data loader, and from GPT to model, I'm importing GPT-2 web model, and here, just so I can access a few functionality by providing typecasting, I'm also importing torch.utils.data import data loader, because when I provide it as init parameter, right, I can access a few functionality here. It will basically give me autocomplete. That's all. Um, from torch dot optim, we need an optimizer, right? So I'm going to use AdamW with weight decay. I'm going to use AdamW. Um, import torch dot nn as nn. Import torch dot nn dot functional as f. These are some common imports. I'm not sure even if we are going to use a few of these. Um, from tqdm import tqdm import torch finally. Okay, so this should be here. Okay, looks good. Now let's try to create the trainer. Okay, sorry about that. um class GPT-2 trainer, which will have an init function, which will have a model, which will be the GPT-2 web model, which we already created, and train data loader, which will be a data loader. Okay, so these are the two parameters, and here self.model will be equal to model. And now if I highlight the model, right, it will give me the values of, like, the characteristics of GPT-2 web model, which is an nn.module. Okay, so if I call forward and all, it will work basically. Okay, so then we have self.train data loader, which will be equal to train data loader. All right, now time to initialize a few function, which is self.device equal to device, self.learning rate equal to learning rate, self dot number of training epochs, which is equal to number of epochs, and then self dot batch size which is equal to batch size, and then self dot weight dk equal to weight dk. Okay. Here I need to import two things. One is a loss function, which is gonna be, if you all remember, nn dot cross entropy loss. Right? I've already told about that and why we need to use this. Please watch the pre-training guide if you haven't watched yet. And for optimizer, we are going to use AdamW, for which you need to provide the parameters which you are going to optimize, which is the model parameter, self.model.parameters. Here you can see, right? The parameters completion is, it is showing for me here. That is why I had those as typecasting. Okay. So not typecasting, type identification. Let's put it that way. Self dot learning rate, and then we have weight dk, which is self dot weight dk. Okay, all of these values are provided. Now, what I'm going to do is I'm going to create a few functions which will complete. Okay, train one step for which it will have self, and then the input batch it needs to train for, and then train one epoch, which should basically have self alone. And this input batch as well, what we can do is model forward will have a few optimization to get the loss. So let me put it as model in batch, which will take again self comma input batch. Okay. And here also I'm going to have it as pass. Finally, these are just going hierarchically, right? So finally, def train of self, and that is going to be starting with this. Okay. First, to track the global steps we are going to calculating, because sometimes if data is very less, we do training for multiple epochs. So to calculate global step, it is very important. So next, epoch losses track. So basically, I need to have a list of loss at each epoch. So that is here. And then epoch losses. Okay. So what happens in epoch losses track and what happens in epoch losses is that in epoch losses track, whatever loss was there in each epoch, that will be there. And in epoch losses, loss at end of each epoch, that will be there. Okay. Now, since it is training, like I said, we might train for multiple epochs. So it will be for epoch in range of self.num epochs. What we'll do is first we'll add a login here, printf string, where I'm gonna say I'm running epoch number. Okay. Let's put it +1 because it is gonna say 0. It doesn't make any sense. Let's put it that way. And then here, okay, I'm gonna assume that in train one epoch, I'm gonna get a few values which I require. Like I said, the train losses, the steps completed, how many steps completed, so that I can update the global steps. Okay, steps completed count, and then epoch loss. What was the loss at the end of the epoch? Okay, epoch loss will be equal to self dot train one epoch. This is just so you know. Now I'll know what I need to expect in train one epoch. That is why I usually go in this way. So here, epoch losses track, I'll append it with train losses. and then epoch losses. In that, I'll append the epoch loss. Okay, so basically, if you plot the graph of epoch loss track, you will get the loss curve. Okay. Next, global step will be updated with steps completed count. Okay. Um. So after this, finally, we can do a few logging. I'll just pause it now, and then I'll just put that logging. Okay. I'll write it because if I'm gonna type it, it'll take a few minutes. Okay, I've typed it. Here you can see. So I'm just basically saying completed epoch number, whatever epoch it is, epoch stats. So this is the train loss at the epoch, and then this is what this step is the step I've completed right now. Okay. So here, you can see the train is done. We'll go one step below, which is to train one epoch. Here, what we need to do is we need to set the model to train mode. Okay. And then here we need the train losses, right? So basically, this train losses will come from train one step. So basically, whatever loss we get there, we'll just append it to train losses, and also steps done. Steps done equal to -1, so that we can provide the steps done as well. So for input batch, so we are getting the input batch from the train data loader, self dot train data loader. I'm gonna add a TQDM there. Okay, because that is when we'll know, like, how long the training will go actually. um Loss equal to self dot train one step of input batch. Okay, so basically I'm expecting that the loss, I'll get it from train one step. um then what I'm going to do is steps done will be equal to um plus equal to 1, because one step is done here. And then train losses dot append of loss. Here, the epoch loss, which we need to calculate here, will be equal to sum of train losses, whatever losses I have right now, by the steps done. Okay. Um, so I'll return these train losses, steps done, and then epoch loss. Okay. So now you can see in train one step, I'm expecting a loss, right? So here in a training loop, what happens is first we set optimizer to 0 gradient. So that is done. Now next what we need to get is the loss. Okay. So there what I'm going to do is I'm going to call model input batch of input batch. Okay. Assuming I get the loss, I need to do loss dot backward. Now you can see it is not highlighting, right? If I did loss is to nn dot cross entropy loss. Oh, still it is not doing, maybe. Okay. Seems like if I don't do a return type, it won't work. It's fine. No, not an issue. Let me keep it that way. So backward propagation starts. Now I need to update the gradient based on that. So for that, self.optimizer.step. All right. So all I need to do is just return the loss. This is what happens in one step of a training. And in one step of the training, what happens is you also do model forward, right? That we'll see here. Okay. Model inputs will be equal to input batch of input IDs. We'll make sure that it is in the device. Okay. Self dot device. Similarly, we need to do it for labels as well, so that loss function doesn't give any issue. Okay. Now these two are done. I need to get the logits, which is the model output. Self dot model of model ints. And here, if you see, like I told here in the model, where is it? Here it is. If I provide return attention weights to true or not, doesn't matter. At least a none will come. Okay. So basically, what we can do is logits, comma, attn weights. So that is going to be self.model of. And then here, we need to do that shift, which I said. Shift logits will be equal to logits of batch dimension, whatever it is, doesn't matter. And here, till last, I'll take in the tokens, and the embedding dimension is going to be same. I'm not going to touch it. Since I'm changing the structure a bit, so I'm just making sure that it is contiguous. And in labels, shift label is equal to logits of, again, batch size doesn't matter to me, whatever it is. And then from first token, I'm going to take till the last token, so that this forces it to calculate the loss based on the next token. Okay. Now I'll get the loss. Okay. Loss is equal to self dot loss function of shift logits dot view of -1 comma shift logits dot size of -1. Okay. And then shift labels. Oh yeah, I think this is where it is. Shift label dot view. I guess it is view of -1. Okay, so everything will become a single token. Okay, so it will be, if it is something like this, it will become something like A S, like this. Okay, so that is what happens here. That is when it can compare the tokens, and then it will aggregate a value in state, like this is how it is deviated. So now we have the loss as well. So we are not going to do anything with the labels. I think we did something wrong here. Here it is. I just copied it, but I didn't change it. It's fine. Attention rates are not going to be used. That is not an issue here. So right now let's test it. Okay, it is around 70 times function. If dunder name is equal to dunder main, first we'll create the model equal to GPT to web model, and here I'm making sure that it is converted to device. Okay, and train data loader will be equal to create train data loader, in which I need to provide the path, which is mini GPT-2 pre-train data slash final JSON data slash, and then it can take all the values from there. If you remember, I told, right, we need to put that slash for must. Trainer will be equal to GPT-2 trainer, for which we need to provide model and train data loader. Both are provided. And if I call trainer dot train, here you can see, actually, if you see, this function doesn't have a save checkpointing, nothing is there here. Okay, apparently we didn't use these two imports. That is fine. So let's see if this works. Usually this is how I train, but I might have missed a few. here and there. Dummy train, it is giving me some issue. That is warning. That is not an issue here then. Okay, it is showing me 7 minutes. So what I'm gonna do is I'm just gonna leave it here. Okay, I'm just gonna stop it. So because actually it doesn't have any save function at all. So what I'm gonna do is I'm having a function which I already created, a training loop. Let's put it that way, which is a realistic training loop. Okay, GPT-2 train.py. I have already created that code. I'm just going to explain that now. Okay. So here you can see this is why I didn't actually write it here. It is a 300 line loop actually. Okay. Oh, it is not 300, it is 400. That is fine. Um, the thing is, these are the imports. Let me explain the imports a few here. Um, these are the inputs which we already did. Logging is to log. This is to provide the type, what it is there. Torch we know, and torch distributed in that we import as dist because this is how you can do a distributed training. In training, it is not always you can train with a single GPU. In pre-training, you have multiple GPUs, so you need to do strategies like DDP, FSDP, you can use deep speed. For all of those, you need to use a distributed function. Data loader, like I said, there is DDP here and there is a grad scaler. So basically this is used to scale the gradients. Okay, sometimes the gradient will go like 400 and all. We need to scale that down, so that is why there is a grad scaler. A tensor board logger, which is summary writer, and then a linear LR scheduler, which is linear rate scheduler, for which there is get linear schedule with warm up. And in Torch distributed FSDP, there is methods like FSDP, and then there is sharding strategy. So basically, what happens in FSDP is your model will be sharded across your GPUs. Unfortunately, I can't show any of these here. This is a function which I generically wrote on an assumption that you guys have a multi GPU. Unfortunately, I don't. Okay, but this code should work. If it doesn't, hey, you can just let me know. I'll try to help you out. Okay. Unless and I mean, like, if you have a multi GPU, let's put it that way. In FSDP, again, there is auto wrap policy. This is to wrap the models for FSDP instance for transformers. Okay. Um, there is other imports like NumPy, Seaborn to visualize the attention mask. Um, so to show that there is PyPlot, and then for progress bar there is TQDM and JSON and all. And here you can see this is the default config. Oh, sorry, outputs for output directory, logs for logging directory, number of epochs. Let me put it 1. Learning rate is 5 minus 5. I can also keep it as 2e minus 5. Anything is fine. I'll just keep it for 5e minus 5. Weight decay 0.01. Warm up steps 10 is more than enough. Gradient accumulation steps is 1. So wait, if you don't know what is gradient accumulation steps, gradient accumulation steps is a parameter which will control at how many steps you want to do back propagation. Okay, that is what is gradient accumulation steps. And then max grad norm, like I said, it will clip the gradients to some scaled value. Mixed pressure, I don't want to do it in mixed pressure, which is FV16 or BF16. I don't have that good GPU. Parallel mode, like I said, if you have a good GPU, you can do mixed pressure and parallel mode, which is DDP, FSDP, deep speed. You can enable one of these. Unfortunately, I don't have GPU to do that, so I'm just keeping none. Checkpoint interval, I'm not sure how many checkpoints we have. Like I said, this is a code I have written already for another use case. So I'm just going to adapt those actually. Okay, so let me put it as 100, no, 400 maybe. I'm not sure how many steps we are going to have. And at 400 steps itself, show me an evaluation. At 400 steps, show me an attention visualization. We are going to ask everything from the model. Um, with pre-training, there is a functionality which you need to provide, which is resume from checkpoint. So what and all you need to do in training group, please watch the theory video which I've already made on LLM pre-training. At that time only I created this code actually. um, so these are some important things which should be there in a pre-training code, okay? Because sometimes your GPU connection might go off, so you need to resume from checkpoint. Let's say it is for 1 month pre-training, and you are done with, let's say, 20 days, and it is getting stopped. Okay, so at that time, what you'll do is you'll start from the 20 days, whatever latest checkpoint you have. So that is resume from checkpoint. Right now, it is none because I haven't trained yet. Um, a local rank function to get the local rank. Like I said, if it is multiple GPUs, you'll get a local rank, but I don't have a multiple GPU. Deep speed config is none. FP16 enabled as false, but you can make it true if you set expression to true. Logging steps is 100. At every 100 step, I need to have the loss and all. Okay, so here you can see I'm just getting the configuration, self.setup directories, which will make sure that there is output directory and logging directory so that things can be stored there. Initializing the model, training data loader, evaluation data loader, setup distributed, which will do a distributed setup. Okay, so here you can see um, first we get the device, and if it is DDP, first you need to distributed.init process group, for which you should use a backend known as an NCCL. If you're using CPU, I think there is a backend known as Glue, if I'm not wrong, I'm not sure. For which you need to provide your device IDs. Like, local rank will say what is the device you are there, and there is a world size. So how many GPUs you have, that is also there. I don't want to install deep speed, so I wrote the code and then I commented it, but this is how you can do. Like with deep speed, you need to provide the optimizer as well. Okay. Um, for FSDP, first you'll get the mixed precision policy, and then you'll enable it with FSDP, where you need to provide model, your mixed precision policy, and then sharding, like how you want to shard it, your auto wrap policy, and then backward prefetch. Okay, all of these needs to be provided. And if you're doing a simple, a single GPU training, just do model to self the device, and that is more than enough. Okay. Next, it is to set up the training components. For training, you need, your optimizer. Like I said, if it is not deep speed, you need an optimizer from here, which is Adam W, and we are making it like before, but we are also making the number of training steps. We are calculating it. So basically, it is going to be length of the training data loader with multiplied with the number of epochs, and the scheduler is going to be provided with the optimizer. So basically, what it will do is it will change the learning rate of the optimizer at some time. Okay, it will have a logic behind. So it is a linear logic here. But yes, it will differ with optimizer. There is cosine, there is linear with warm up. We are using linear with warm up. There is also something known as reduce LR on plateau. So what it will do is when the training loss becomes not changing a lot, 0.1, 0.11, 0.9, 0.9, in that range, it will try to reduce the learning rate. There are different types of learning rate scheduler, and one of those is this. Okay. And here I'm just saying that the warm-up steps, like what it will do is warm-up steps till that it will not change the learning rate, and after that it will start to change the learning rate according to the loss function or loss we get. Okay. So num warms and warm-up steps is here. Grad scaler, like I said, it is to scale the gradients, and then loss function is cross entropy loss. Okay. So these are the important things. Other than that, we are having a function to load the checkpoint if you want to resume your training, and we are initializing a TensorBoard logger, which will save it in the logging directory. So for load checkpoint, if you see, we'll load the model, optimizer, scheduler, and which step we want to start. All of these will be obtained from load checkpoint. Okay. And if you see the save checkpoint, it will have all of these information. Okay. Step, model, state dict, optimizer state dict, scheduler state dict, loss, config, everything will be there. Okay. So these are the primary things which you need to do. Now let's go to the train. So there are other functions here, but right now let's start with the train function. So you can see there is a logging stating that, like, we are starting the training. We are getting the global step, setting up a progress bar with TQDM of len of data loader with the number of epochs. And here for epoch in range of number of epochs, we are running up the loop where we are setting up the train model to train function trains mode. Epoch loss is set to 0. We are going through the batches in data loader, and since we put enumerate, it will give step and batch. If not enumerate, it will give the batch directly. Here we are calling the train step. We'll go through the train step later because it is going to be the same, almost same as what it was before in the dummy train as well. So here we are providing the batch and the global step. Along with that, we are just getting the output loss, which we are adding with the epoch loss. Okay. And then here if you see, we are just seeing, like, when we want to log, and if we want to log, we'll log these metrics, which will be sent to the log metrics function. And here you can see in log metrics, first, those values will be added as scalars. Added scalar, it's just a value adding function in TensorBoard. So that is about that. And in model parameters, so here we are just adding a histogram for whatever parameters are there, and for gradient norm we are adding a scalar again. So for visualization attention, once we get the attention map, so here you can see the attention maps are there. So this is just for the evaluation set. Okay. We get the outputs, and we are saying output attention is true, and here we are getting the attentions of layer -1, and we'll just see the attention map. So basically that is about attention map, so to speak. Here right now, consider continuing with the training loop. Let's come to the train step later. Here again we are seeing, like, when we want to evaluate, and if we want to evaluate, we'll evaluate, and then we'll also log those metrics. And also we'll see, like, when we want to save as checkpoint, and if there is a saving required, we'll go to the save checkpoint, and then we'll do save checkpoint as well. And here, once these are done, we'll add the global step one step forward, and then progress bar will be updated. And here you can see epoch loss is calculated by dividing with the help of train total loader length, and then the logger is there to log. And then we have our metrics here, eval metrics, which is to call the self.evaluate. And that eval metrics, whatever we got, will be logged, and then save checkpoint will save the checkpoints basically. And then once these are done, we'll close the writer, which is the logger. Okay. Okay, looks good. So right now what I'm going to do is I've kept the config at two places because this is like the default configuration, and if I override this, I can, if I want to override this, I can override it at the bottom. Okay, that is how this is set. So basically I don't want to do that, so I'm just going to keep it like this, config. Okay, now it looks good, and the path is going to be mini gpt to pretrain data slash what is that? I think final JSON data. Final JSON data. Still, the data set is going to be the same data set as before. So that is there. When we call the train function, if you remember, the train step is not seen yet. So if you go to the train step, first we'll see if there is some expression which we need to do. If we need to do, then we'll do an autocast, and then we'll make sure that it works for um, some expression. And if not, the pipeline will go here. Okay, the pipeline other than that remains the same actually. Okay, here you can see model will be there. We'll be sending our batch IDs, and then we'll get the loss function. Once the loss is done, we'll divide it with the gradient accumulation steps, because like I said, you'll accumulate it, right? And how that accumulation happens, here you can see. Okay, if it is equal to 0, at that time only you'll do the back propagation. Like, basically back propagation will happen, so that gradients will be stored actually in the loss itself, and optimizer at step will then optimize the parameters. That is how gradient accumulation step basically works, and then we'll get the loss function. Okay, and when you go for evaluate, this is the function. um Outputs, comma, attention weights. Okay, um that is fine. And in visualization attention as well, outputs, comma, attention weights. Let's put it this way. Hopefully this should work. Um, so yeah, these are the things which are there. So if I call, sorry, Python GPT-2 train.py, it should start the training without an error, hopefully. And also, guys, this same code will execute in Google Colab. If you don't have a local GPU, please don't run it in local. Uh, just take these code, implement in Google Colab. That's all. Simple. Okay, there is 7,000 steps apparently. Okay. People object has no attribute view. Okay, yeah. Outputs, comma, attention weights. I changed it and I didn't change here. That is my mistake. 7,000 steps. I'm not sure when it is going to end. Mm, okay, it is showing me 8 minutes apparently. So what I'm going to do is I'm just going to leave this like this itself. So, like I'll just make sure that this is made fast. Okay. But here you can see loss is decreasing, right? 8 to 4, it is decreasing. So I'll just leave it like this. Let's see where we end up. At least if it is 1 or 2 at the end, I'll be very happy. 3 is also fine by me. Okay. Let's see at the end of you know the training probably. And here you can see logs is printed and outputs is saved. Okay, so all are there. Let's see. I'll just keep it like this. So let me see if there is any logs here. There are logs, and here you can see that many checkpoints. So what we can do is tensor board. Is it there? Yeah, it is there. Tensor board -log dir guess is equal to logs. Let me see if the board has all the logs correctly. So here there is a tensor board. Let me show you right now. So I hope the tensor board is actually visible. All right. So here you can see that the loss, it is getting down. Here you can see. So it was something like this, and here you can see the good point is it also shows time actually. Okay, so it started from somewhere 5 and it has gone down. If I smooth it, here you can see. So this looks like a good loss graph. Even if I do training, it will go here and then stop somewhere. Okay. So those are the scalars, and I can see like epoch. We didn't do multiple epochs, so it is going to be a single epoch, right? As far as the learning rate is concerned, it started from 4.94 e minus 5 and it ended up somewhere at 2 e minus 5. So that was about the learning rate. And the train loss, it is coming up from 6.177 to the final one being around 1 point, smoothed 2.269. Yeah. So that is, yeah. So that is all about the training loss and all. But what we are going to do is we are going to have another day where I'm just going to show you how you need to understand the evaluation. Okay. So next video will be about the perplexity theory and how you can calculate perplexity and visualize attention weights and then make some inference out of it to understand how basically things work. And here you can see the value is 1.628. That is the loss we ended up with, and that is a good training loss. So next video is about inference and then moving up to different things like that. Okay. I'll see you all in another video. Until then, happy learning. During training, a very important step which is usually not given a lot of importance is none other than the evaluation step. Here, I have created a perplexity evaluator where we'll try to evaluate the perplexity of the model. Also, we'll try to understand how our model does attention. Why is this? When you give perplexity, you will understand what or how much the model is confused to see a new data. I'm not expecting a great performance here because we have just trained it with 7,000 samples. That is nothing. But right now, the aim is to understand the working, right? Not to pre-train an LLM exactly, so to speak, because I don't have that good resource. So here I have written a code which I'm going to explain you now. This is not needed. So let me start with the evaluation first, and then I'll show you how you can basically calculate the perplexity, how you will visualize the attention, and also as a bonus, we'll see some inferences as well. Okay. all are going to be there in this video. So stay till the end and have some fun playing with your video, your own model. All right. So as a recap, what we have done till now in day 8 was pre-training LLM, for which I've used GPT dummy train.py, where I have done some updation and all. With those updation will be there in the GitHub. Okay. And then there is also a GPT-2 train.py file, which has all the capabilities, which we have seen in detail in day 8. Now it is day 9 and we are moving on to evaluation, because the training 1 epoch is done and we are at around 7 laws. So I'm expecting a lot of repetition because the training started at 10, if I'm not wrong, and then it ended up at 7. So I'll say the training is working, but it needs more data for it to understand. Okay, let's see how much it is confused right now. So for this, what you need to do is first create a test set. And here I have a test set of 10 samples, and then I've created a class which is perplexity evaluator, in which I'm having 3 parameters. One is model, and then a tokenizer, and then device. All right. And the model is nothing but the model which we have trained already. Tokenizer is the tokenizer we used while we trained, and the device in which I want to perform this evaluation. So I wanted to do it in, let's take that out. I wanted to do this in GPU so that this will be faster, but you can, if you want, you can do it in CPU as well. It will work. All right. All you need to do is just change this code out to CPU. So what we're doing is, first we are getting the model, changing it to device. So basically the model will be initialized in CPU, but we are converting it into GPU, and then we are setting it in evaluate mode. Okay. And then there is a function which is calculate perplexity, which is helper function used in evaluate dataset. So evaluate dataset is a function which will take a list of string as input and will provide perplexities as well as attention weights. Right now, we don't care about attention weights. We'll care about that later, but we care about perplexities right now, and that is what we are going to see. Okay. We go through each of the text and then we calculate the perplexity, and then we are just appending the perplexity. That is what is happening here. So in calculate perplexity, what happens? So before going into that, it is very important that you know what is perplexity. Perplexity is the factor at which the factor basically shows how much your model is confused to see a new input coming up its way. That is what is perplexity. Higher the value, worst it is. So lower the better. And here, if you see, we are having the tokenizer where we are encoding the text, and then we are returning the tensor as PT. That will give us the tokens, right? Now we are providing this to the model. We are getting the attention weights as well. Here we are calculating the loss function, for which, if you remember in the last video itself, I said we need to do shift logits, and that is what we are doing here. Okay. And if you want to see that, it will be there in GPT-2 dummy train. If I go to the loss, here you can see, right? This is how shift works. This basically forces to next token prediction. Okay. And then here, if you see, it is shift logits dot view of -1 comma shift logits dot size of 1 -1, and then shift labels dot view of -1. Basically, like I said, it will convert it to tokens of tokens. Now you are calculating a cross entropy loss, right? This cross entropy loss basically will be exponentiated. That is what is perplexity. Okay. And we are calculating this for all the text which is available. Okay. So there is another function as well, which is visualize attention weights. So how that happens is, we are getting the attention weights here, right? We'll be sending that in this. All right. In that, what we'll do is, we'll take the 0 of every layer in head, which we specify. So for example, right now I'm most interested on knowing about the last layers first state. Okay, because last layer's first state usually has a lot of information to it. So we are taking those attention weights, and then we are basically detaching it from GPU, making it CPU, and then converting it into a NumPy array. We are converting the tokens as tokenizer. By a tokenizer, we are converting it into tokens actually, and then we are decoding it again. Why? Because if you see, it is a sentence, right? So you need to split it via the tokenizer. So we are doing two process. First, encoding it, which will give the number, and then if we decode it, it will give the token label. Okay, that is what is happening here. Now, what I'm doing here is plotting a figure which is a heat map where I want to see the attention with my x-tick labels and y-tick labels. Basically, it is labels at your x-axis and y-axis as token labels. That is what is there. And CMap is Viridis. Viridis is just a color map. That is why it is CMap. And annotation is true so that it will give the numbers. The numbers is basically the attention focus, okay? And FMT is .2f. So whatever I have, it will be .2.2 float value, okay? After a decimal point, there will be 2 float value. And then I need it as square, okay? So square is set to true. And why is square set to true? Because since your x and y axis are the same, basically it will give you a square, right? And also here, if you see, the x-axis is rotate as a 45 degrees. So basically, instead of writing like this, it will be right like this, okay? That is why. And we are saving that figure as well, okay? So this is the visualization section, basically. And in the main section, first we'll load the torch model, and then we'll create the instance of the model, and then we'll load the static. Okay, in this, the static will be there, and then we are loading it via this load static function. And here is the tokenizer as well. Here we are calling the perplexity evaluator, and then we are creating a test data set. So if we call the create test data set, it will just return this list. Okay, now what we're doing is we are calculating the average perplexity, and then also we are visualizing the attention weights of last layer's first state. Okay, so now let's see the output. Okay, so I haven't actually tested yet, so I'm testing with you all. It might be unbelievable, but I haven't, just to keep my reactions natural. I'm not expecting a lot out of the model. At least if it gives a perplexity in 3-digit, I'll be very happy, but it gives in 4-digit, that is not very good. Let's come to the perplexity later. First, let's see the attention, right? The is giving the most importance to the, quick is giving the, and quick has a lot more importance actually. Basically, the gives quick gives more importance to the actually, okay? Because here you can see query tokens are here, key tokens are here, all right? And here you can see, right, everything is 0 because that is how the mask is. And here if you see, once it goes down the line, right, the first token, which is the, has no value literally, okay? And when it comes to dot, literally no token plays any role except dog, okay, which makes sense. But when it comes to this dog, right, the has played a lot of role, not lazy, because the dog sounds something similar, maybe that reason, I'm not sure. And here you can see there are other examples, okay? Apparently here you can see, right, comma is having no importance here. So yeah, basically it will print the attention attention weights for literally every test which we created. Basically there are 10 samples, so 10 there. So here there is another thing which you need to see. The average perplexity is 5044, which is literally doesn't make any sense for me. The perplexity usually lesser is good. At least I was expecting in 3-digit, let's say, or like a 500 or something like that, which would make some sense. I'm not sure what this model has learned. When the loss was 7, I didn't expect a lot of it to learn. But yes, this is not something I expected, but it's fine. We are just getting this started. And if you want to train this as a real model, a full-fledged model, let me know. I'll put some, what can I say, resources, and then I'll take up a GPU, cloud GPU, and then I'll train it probably. Okay, so let me know on that fact. So yeah, now let's go with this inference. So if you want that, right, just hit the like button, and if this video crosses 100 likes, even if you don't say, I'll train it for a full model. Okay. For GPT-2 inference, the model is GPT-2 web model, and the device is CUDA. I'm inferring it in CUDA, and I want 100 tokens. Okay. So basically, I've provided my model, device, max length, and tokenizer. So if you're wondering, this is inference. Okay. The model is set to device, and then it is set to eval mode as well. Now, when we call the generate text function, we are using a greedy search where we'll first encode the prompt or input whatever we have with the help of tokenizer, and then it will be converted into the device in which we are inferencing. Here in this case, it is CUDA. Right now, we are starting from input IDs, right? It's like a completion. So generated sequence start from there, and we are running a try loop where with project.nograd for our underscore in range of max length, which is 100 tokens, which will be generated. All we are doing is we are getting the input IDs, sending it to the model, and once we get the logits, we'll do argmax. Okay, so argmax will say which logits, if you see, has the probability for all the tokens which are possible to be the next token. So for example, after lazy, it could be human, it could be dog, it could be cat, anything. For each of those, probabilities will be there. And here we are getting the argmax, which is the most probable one, and that token is concatenated to the sequence which is there, and then this loop will run again. Okay, unless and until we have a end of sequence token, this loop will run, and finally once the loop breaks, we'll decode it. Okay, so that is what is happening here, if you're wondering. Okay. All right. And here, if you see, it is just GPT-2 inference. I'm just saying the future of artificial intelligence, at least if it says something like first is, these are just net inferences. Okay. Like I didn't write this inference code. This is from Claude AI. I'm just being very honest. Okay. And if I run this, I think I should get an error. Yeah. Output/model.pt. Please give me something. And the world of the most of, okay, it is a future of the artificial intelligence. It's trying to repeat something. Yeah, and I can get from where it is coming. And the world of most of the something like that it is trying to say. So our model is repeating. It's fine. We can train this for longer time. That is there. We can increase the layer, we can increase the hyperparameters, that is all there. But the aim of this series has been to understand how you can train the model, and this is how you train the model. So yeah, I'm happy with what we have started, and I see a good potential here. So yeah, let me know. You try to train your LLM and let me know how it went, and soon we'll see on how you can adapt a model to a different task. Okay, so next video will be about, or the next day, it's gonna be about using this model to train a sentiment classifier.